Okay, so with this lesson, what we're going to do is look at transformations of those exponential functions. So similar to all those other types of functions we've done, we can take our base exponential function, which was of that form y is equal to c to the power of x, which we did in class on Tuesday. And what we can do with that is now just to apply our transformations like we did before, right? So our base function was that y is equal to c to the power of x, okay? And now we can apply those transformations similar to as we've done in all those other types of functions, right? So we've got our a value here, which once again represents our vertical stretch, which is going to affect your y values, okay? You've got your b value, right, which you can see up in the exponent because it's affecting your x values, and again, it's going to be the reciprocal, right? So if you have a b value, your horizontal stretch is going to be the reciprocal 1 over b, right? So if that value was 3, your horizontal stretch is a third, okay? Same thing here with your h value. It's defined as x minus h. Again, it's in your exponent because it's going to affect your x values in your coordinate points, and it's defined as x minus h, so it will just be the value that you see. Okay, and again, your k value is there added on to the end, and that's going to be your vertical translation, which is again going to affect your y values. And specifically, it's going to affect where your horizontal asymptote ends up, which we'll look at in an example here in a second. So if we just look at a couple examples of vertical translations, right, so we started here with our base function of f of x is equal to 3 to the power of x, which is given in the graph in red, right, and now we've only applied vertical translations. So we've just added on that k value, so we've got 3 to the power of x plus 2, okay, and what you should see in this graph here is that in the base graph, your horizontal asymptote is here at y equals 0, okay. When we apply a vertical translation of plus 2, it shifts the entire graph up, so now our horizontal asymptote is at y equals 2, and of course this affects where our y-intercept is going to be, right? So as opposed to being down at 1, it's been shifted up 2 and it's now at 3. Same thing happening here in the green graph, where you've got 3 to the power of x minus 4, and if you look carefully at the green graph, its horizontal asymptote has been shifted to y equals negative 4. Okay, and then again, that's also affected your y-intercept, which now has been shifted down 4. Okay, these vertical translations are going to affect obviously your y-intercept because they're y values, and your horizontal asymptotes, which in turn will then affect your range. Okay, when you get a shift that's moved all the way down, you will see that now in this green graph there is an x-intercept that can be solved, right? And we can do that here by taking our h of x function, which is equal to 3 to the power of x minus 4, setting our value, our function equal to 0, right, adding 4 to both sides, and then you would estimate a value of x, trying to figure out 3 to the power of what would equal 4, and that would just be a guess and check for solving there, okay? So again, if you've got a vertical transformation, it could result in x-intercepts, but from our base functions, we discussed that they don't have x-intercepts because the horizontal asymptote is at 0, okay? When we apply horizontal translations, right, again, we see those here in the exponent, and they happen in the opposite manner. So we see there it's x minus 3, right, but that results in a horizontal translation of 3, right? So we see there in the purple graph that this entire graph has been shifted 3 over. So instead of that y-intercept being at 1, right, the y-intercept shifts down, but really what's happened is the graph is shifted to the right. So that point there, with the y value at 1, it just moves. So now instead of it at 0, 1, it's at 3, 1, right? So the x coordinate is changing, right? So if you're looking at it as a mapping rule, right, your x coordinate is having that h added onto it, okay? And then your y values have stayed the same, okay? And then same thing in the black graph, you've got h of x is equal to 2 to the power of x plus 1. That's your horizontal translation of minus 1. So again, you see that that value has been, 1 has been subtracted from it, right? And then it's just kind of shifted 1 unit to the left. Okay? Again, that's just more examples that you can take a look at and see how things have changed with the mapping rule as well as with the graphs. Okay? If we look at the stretches, again, vertical stretches, those are coming in the form of an a value that's out in front, and again, it's just being multiplied. Again, it's affecting your y values, right? So your mapping rule will go x, y, maps to x, and then a times y, okay? Again, that is going to affect your y-intercept, right? So looking at your values here, right, in blue you've got g of x, which is 3 times 1/2 to the power of x, and now your y-intercept is at 3, right, because anything to the power of 0 is 1, and then 1 times 3 is 3, right? No other transformations are being applied, so that's now our y-intercept is at 3. In our green graph here, again, it's 3/4 times 1/2 to the power of x, right? So again, 1/2 to the power of 0 is 1, times 3/4 gives me that y-intercept there at 3/4. Negatives, again, we know that those are then reflections as well, reflections in the x-axis. So even though this 1/2 would show a decreasing function, because of the negative and the reflection, we now see that this orange graph is in fact considered an increasing function instead. Okay, same thing's happening here with purple, right? So even though that is 1/2, and we would say that because it's less than 1, it's a decreasing function, because it's been reflected due to that negative, it's now an increasing function instead, where the y-intercepts are with the original orange graph -4, which we can't see on the graph, or -1/3 here. Okay, so again, typical, similar stuff to what we've been doing before. Right, horizontal stretches, you'll notice this one looks a little bit different in that they all have that same y-intercept. They all keep that y-intercept at 1. Again, because if x is 0 in any single one of these options, because you're just applying a stretch, you're multiplying by 0, so your exponent remains 0, and anything to the power of 0 is 1. So your y-intercept is 1 in every single one of these equations, right? And again, we do see here in the orange and the purple graphs, right? Again, we have a reflection across the y-axis, right? So again, what that does is it does flip our increasing or decreasing, right? So we would look at the orange and purple with ratios of 2 and think, okay, well, it's greater than 1, so it's an increasing function, but because of this reflection that's in both of them with the negative, it then turns, and you can see that in your purple and your red, or purple and orange, sorry, that this now does become a decreasing function instead, okay? So it does go down. And once again, you're just dealing with stretches that are reciprocals as well, right? So if we look at that one there in blue, right, it's 2 to the power of 3x, which that's going to mean that there is a horizontal stretch of 1/3, okay? This 2 to the power of 1/3 x, that's going to be your horizontal stretch of 3. And this, again, we'd say that there's a reflection in the y-axis and there's a horizontal stretch of 1/2. So what you're seeing is that you are seeing that those graphs are becoming more either compressed, or appear to be increasing at a faster rate, or stretched out, increasing at a smaller rate. Okay? So that's your stretches. And again, just a couple more notes with more examples, and again, seeing how that happens in your mapping rules. All right, so let's now take a look at an example. So if we go off the base function y equals 3 to the power of x, and we try and look at the examples down here in A and in B, okay, we're going to look at those and we're going to do a few things. So the first thing it's asking us to do is to state the parameters, okay? So the parameters are actually stating what are the values of A, B, H, and K, right? And what are they actually doing? So in this first one here, right, so we've got this A value here of 2, right? And that results in a vertical stretch of 2. And the only thing that's happening in the exponent is this -4, right? So that's an H value of 4, which means we have a horizontal translation of 4 units to the right. Okay, so those are the parameters, are the values of A, B, H, and K. So in this case, only A and H. And then what happens with those transformations, right? So the A value of 2 gives a vertical stretch of 2, K value of 4 giving a horizontal translation of 4. Okay, those can then be used to create your mapping rule like we've done before, right? So your x, y coordinate from your base graph will turn into x plus 4 and 2y in your new transform graph, right? And the table of values is already given here. So if we apply that particular mapping rule to this equation of 2 times 3 to the power of x minus 4, right? And we look at their corresponding coordinate points, right? That first point of -1, 1/3, you're going to take that -1, place it in for x, and it's going to be -1 plus 4, which now gives you an x coordinate point of 3, and the 1/3 is going to get multiplied by 2, giving you 2/3, right? Doing the same thing with the other points, right? That point there of 0 and 1, 0 plus 4 is 4, and 1 times 2 is 2. Right, next point, 1 plus 4, that's 5, 3 times 2, that's 6, 2, 9, so 2 plus 4 is 6, and 9 times 2 is 18, and finally 3 plus 4 is 7, and 27 times 2 is 54. All right, so that would be like your new table of values, right? You can use that to then sketch a graph. I've got the graph already on the next page, right? And again, in blue there you can see the original y equals 3 to the power of x, and in red you've got that transform function of y is equal to 2 times 3 to the power of x minus 4. All right, now looking at those properties, your domain remains unchanged. They're both having a domain of x of any real number. Okay, your range is also unchanged because you still have that same horizontal asymptote at y equals 0. It's the same for both, which means your range is always going to be greater than 0. Right? What has changed though is your y-intercept, right? So, and of course obviously you can see that it has been shifted over, right? So that kind of point there at 0, 1 would have moved over here to this point, kind of over 4, but it's also been stretched up 2 as well. Okay, so where this new y-intercept is of the red function, the transform function, you can just evaluate that as you would, right? So substituting x is equal to 0, so 2 times 3 to the power of 0 minus 4. So that's 3 to the power of negative 4, right? Recalling your exponent laws, that's 2 times 1/3 to the power of 4, which is equal to 2 times 1 over 81, which is just 2 over 81. Okay, and that's where that 2 over 81 is coming from, just using exponent laws. Right, so you can let's take a look at all of those things. Okay, so again, it does ask you to describe the effects on domain and range, which we have done. Right, I'll let you attempt B for yourself. By all means, use Desmos, take a look at what that graph's going to look like. Again, keep in mind that this negative would indicate a reflection across the x-axis, which means what you initially would have thought would be a growth curve because the ratio is 3 is now going to actually be a decay curve, okay? And you're going to see stretches. And your asymptote, your horizontal asymptote will change because of that vertical translation there. Okay, so just when you do that, keep that in mind. All right, so let's now take a look at an example where we are given a graph in a situation and we have to come up with the equation. Okay, so the context here is that a cup of water is heated to 100 degrees Celsius and then allowed to cool in a room with an air temperature of 20 degrees Celsius. The temperature T in degrees Celsius is measured every minute as a function of time m in minutes, and these points are plotted on the coordinate grid. It's found that the temperature of the water decreases exponentially at a rate of 25% every 5 minutes. A smooth curve is drawn through the points, resulting in the graph shown. And we're asked to come up with the equation that models this particular situation. So going back to when we first started looking at exponential functions, right, the first thing that we want to look at is what type of curve do we have? And it says that it's decreasing, right? We know that we have an exponential function that is decreasing, all right? And again, if you go back to the slides from 7.1, right, when something decreases by a percentage, we talked about how to find the ratio there by taking 1 and subtracting that. So the C value in this equation is going to be 1 minus 0.25, which is 0.75, okay? So that's how we would get that value. So to kind of start off with, that base equation is kind of this. Temperature as a function of time is equal to 0.75 to the power of n. That would be like our starting base equation, right? Now we need to look at the other things that are coming into play, right? One of these things is that it decreases not every minute, but every 5 minutes, okay? This every 5 minutes is essentially like a horizontal stretch, okay? So that's affecting our minutes, right? It's affecting our exponent. So what that does is that turns our function into 0.75 to the power of m over 5, right? Because we get 75% of the temperature remaining after 5 minutes, right? And we're only going to be able to do that if m is equal to 5, and then your exponent of 5 over 5 would be 1. Okay, so anytime you see something that occurs every 5 something or every something time, that's indicative of a horizontal stretch, right? And so that 5 minutes, so that every 5 minutes, that relates to a horizontal stretch of 5, right? So therefore, what goes into the equation is like 1/5 or m over 5, okay? All right, so the next thing to look at here is the fact that we do have a different asymptote, right? We see here that the asymptote is at 20, right? And that's because you've been placed in a room where the room temperature is 20 degrees, so you're never going to go below 20 degrees if the room temperature stays constant. So that T equals 20, right? That asymptote at 20 shows that we have a vertical translation of plus 20. So that's going to mean our equation now has been updated to T of m is equal to 0.75 to the power of m over 5 and then plus 20. Okay? The last thing to look at then is determining whether or not we have a stretch value, right? And again, we've talked about this before. Yes, you could potentially have both a horizontal stretch and a vertical stretch, but in this case, it's easier just to deal with potential horizontal or vertical stretch, sorry. And we use that by picking a point off the graph. And the easiest point to pick off of this graph is that initial time in temperature. So at time 0, your temperature is equal to 100 degrees Celsius. So you can insert that value of 100 is equal to an unknown value of a times 0.75 to the power of 0 for your time divided by 5 plus 20, right? And then we can solve this, so we can subtract 20 from both sides. That gives me 80 is equal to a times 0.75 to the power of 0 divided by 5, which is 0. And as we've already mentioned, anything to the power of 0 is always going to equal 1. So that's 80 is equal to a times 1, which therefore means that my a value is 80. So my final equation here is T of m is equal to 80 times 0.75 to the power of m over 5 plus 20. Okay? And again, as we've been going through, we have been solving part B. We have been describing how each of the parameters in the transform function relates to the information provided, right? This asymptote of 20 is that base room temperature. This 0.75 ratio is because it's decreasing at a rate of 25%, so you have 75% remaining. This m over 5 here is due to the fact that it's every 5 minutes, so you have that horizontal stretch. And then this 80 is basically showing you the initial difference between the temperature that it is, 100, and the temperature in the room, which is 20. Okay? So just a couple tips as you are looking at problems similar to that. When you are creating exponential functions that involve those types of transformations, a couple things to keep in mind, right? Figure out the ratio, talking about the tips we looked at in 7.1, right? Is it percentages, is it doubling, is it half-life, all that kind of stuff. Okay, that will help you get your base ratio. Look at the potential of an asymptote, right? Is there a minimum point that can be reached in this situation? If so, that applies as your asymptote in your vertical translation, right? Use that initial value or that y-intercept to help you solve for the a value by inserting that value with an x-intercept or with an x value of 0. Okay? Your stretch, your horizontal stretch is going to be like how often does that ratio occur, right? And that's going to be your horizontal stretch applied as the reciprocal, right? So if something is bacteria populations double every 5 days, right, then what's going to go in your equation is actually 1/5, right? So time divided by 5. All right, and those would be the practice questions involving 7.2, the transformations of exponential functions.